Okay, guys. Resonance. Test 3 material. But we've talked about resonance some along the way, yeah? Resonance handout. I usually put this on golden colored paper because if you can learn resonance and master resonance, that's your golden ticket to success in further future organic chemistry. Okay, resonance. A lot of books cover resonance early on. I don't really get into it too much early on other than what's necessary, chapter 2. And then there's more over in like later chapters in terms of like conjugated dienes. So it's sort of 2 parts. I covered all here. Okay, intro, also called what? Delocalized bonding or pi bonding. This first page is a good bit of theory. And then we'll move into, okay, how do you do this on your paper? How do you work with this stuff? We'll start with neutral conjugated alkenes. Conjugated alkenes. Or it could say dienes, because you got it. I'm talking about 2 different alkenes or more than 2. These 2 alkenes are said to be conjugated. Because if we look at the pi bonds here, you got pi bond, 1 electron, 1 electron overlap. Make pi bond, we see the pi bond shown, but you also have the same thing next door. Yeah, 1 electron, 1 electron. There's the 2 pi bonds, right? But look between carbon 2 and 3 here. You got a p orbital and a p orbital. Are they interacting? Well, you got the same thing all across the board here. You got p orbital with 1 electron. Why do you say these are interacting and these are interacting, but are those not? Well, their answer is they are interacting. They're interacting too. And that's some additional bonding that we see that's not really shown in the standard structure. Okay? We also say that these alkenes are conjugated because the two p orbitals here are lined up and adjacent to and overlapping with the 2 p orbitals of this alkene. And you have a system of 4 p orbitals conjugated. When we start lining the p orbitals up like toy soldiers, we call that conjugation. Lining up and overlapping. Okay? So 4 p orbitals conjugated. A conjugated diene. Is this a conjugated diene? Well, we got a pi bond here. And we got a pi bond here. But are the 2 alkenes so-called connected by conjugation? No, there's a carbon in between, or an atom in between with no p orbital. No p orbital. That's sp3. It's got 2 H's. And so the conjugation is broken. The chain is broken. It's not one system with 4 p orbitals. It's 2 separate pi systems. Yes, you have overlap between this p orbital and this p orbital, make that pi bond, and yes, you have the same thing here. But the 2 alkenes are not conjugated all together due to the lack of p orbital in between. So terminology, this would be called a non-conjugated diene. Conjugated. Which one's more stable? Don't look at the numbers or anything. What seems more stable? Bonding is a good thing. This is extra bonding in here, really, what we have. Extra p orbital overlap is a good thing until we get to where it's a bad thing. Over in organic 2, it can be. In certain cases, but typically orbital overlap is good. You got more bonding here, it should be more stable. We can see stability from, and get empirical evidence of stability from something like heats of hydrogenation, right? If you hydrogenate these, hydrogenate here and here, both of these become 1, 2, 3, 4, 5, 1, 2. Both of these become pentane, the same thing, with 2 equivalents of hydrogen added to either one. But the calorimetry, or the heat of hydrogenation, says that we get more energy from this one. Delta H, no, it's not a delta H, it's a heat of hydrogenation, which is given as a positive number. Delta H would be negative 60 for that one, but it's only negative 54 for that one. Negative 60 means this one gives off more energy when hydrogenated, fully hydrogenated down to the alkane. Why does it give off more energy? Because it contains more energy. The pi system contains more energy. Why does the pi system contain more energy? Because it's not conjugated. Why does this one contain less energy? Because the fact that it's conjugated makes it sit at a lower energy. So when it was formed, it just sits at a lower energy than that one. It's more stable than that. But we can have empirical evidence of that to support sort of our theory. A closer look at conjugation found in conjugated dienes. Well, really, I'm just going to redraw this here. Okay? And talk about the same thing. Hopefully kind of clarify the questions. Number of p orbitals in the conjugated system. The only difference is I've removed the number. Number of p orbitals here? 4. It's the same as above. Right? You see all these 4 p orbitals in conjugated? Okay, you got to see that. Number of pi electrons in the conjugated systems. 4. I drew them up there. There's 1 in each p orbital, right? Okay. This goes back to week 1 and 2. This is just structure. And actually, didn't we ask the question how many pi electrons were in the compound back then, August, September? Same thing. I just didn't say we were doing resonance. But it's all the fundamental structure stuff. We're pulling it together. So you know how you need to be able to assess the architecture of this compound, particularly the pi system, with questions like this here. Which leads to a molecular orbital view. Okay. Molecular orbital, MO theory. MO theory, I don't do much MO theory in Organic 1. In Organic 2, when we look at aromatic compounds, we need to do MO theory. And actually, I'll sort of do a little bit that maybe we should have done in Organic 1 at that time. But if you got these p orbitals, they're all interacting here, so we can show this all like this. Now, I didn't draw in the pi bonds, so don't let that confuse you. I'm considering this a diene. The fact that I drew in these p orbitals tells us, hey, that's a pi bond, so in addition to the sigma bond, we have a pi bond here, right? Okay? I'm just drawing the skeletal, which can be called the sigma framework. Those are just the sigma bonds. And then I'm drawing in the pi bonds, but I'm doing it as an orbital view. Now, molecular orbital theory for this is going to say that all 4 of these are interacting, and it's no longer 4 atomic orbitals. It becomes one orbital. One molecular orbital, okay? And the one molecular orbital is spread out over the entire compound. And how many electrons sit in an orbital is the same answer. 2, right? Okay, so 2 electrons sit in that orbital right there. You see that orbital? I've circled one orbital. And maybe you're confused. I don't blame you. How many orbitals did I circle? See the circle over there?
You circled 4.
No, I circled 1. 1 molecular orbital. All right. About the molecular orbitals. Yes, it's 4 atomic orbitals, but when you get to the MO theory, you no longer have atomic orbitals. The atomic orbitals combine and create molecular orbitals. That is an orbital that's spread over the entire molecule. And now it just leads to one orbital that came from overlap of 4. Okay? I circled one molecular orbital and 2 electrons in that orbital. Now, I'm not going to try to explain any more of this. That's the beginning of molecular orbital theory. Question?
Can you show us what 2 molecular orbitals look like? Is that possible?
2, I would just have to draw another one.
Okay, so then for one molecule, we will always have just one molecular orbital.
No, one molecule could have 6 molecular orbitals.
Can you show us one in multiple?
Inorganic 2 of them.
Okay.
All I'm doing now is just trying to get you to, right? Okay. This is just a little add-on information. I'm telling you that we're not going to do much MO, but I gave you enough to get you confused a little bit so you'll start thinking about it. All right? And I'm trying to do this by saying I circled one MO that came from combining 4 atomic orbitals. But once you combine 4 atomic orbitals, it's no longer atomic orbitals. It becomes one thing. It's one molecule. It's one orbital. And 2 electrons sit there. I told you it's the same number. It's 2, right? Somebody answer 2? That's it. But we don't need to talk about it anymore because it's just a precursor. Question?
So this only applies to conjugated?
Do what?
Like, this only applies when it's conjugated?
That's good. Yeah, good question. We'll mainly only talk about the conjugated molecular orbitals. There's a lot of questions on MOs, yet we're really not covering MO. Question?
I just want to know how you went from 4 pi electrons to 2.
I had the same question.
No, I didn't. No,
Because up there we had 4.
You said 4 pi electrons, and then for that one you said
no, I didn't ask how many total pi electrons. There's 4 total pi electrons.
Okay.
All I asked is how many electrons could fit into one molecular orbital. It's 2. And it's the same answer of any orbital. It's 2. How many electrons go in an orbital? 2. 2. It's the same answer. We don't all of a sudden put 3 or 4 electrons in an orbital. Right? In Gen Chem, you put 2 electrons in an orbital when you were doing off-ball and all that stuff. It's the same answer. Each molecular orbital holds 2 electrons. All right. Good. There was lots of questions about MO. That's the last we'll say about MO in this class. Did I mention MO on day 1 when we talked about oxygen? Oxygen's paramagnetic. It's not magnetic properties, but that's only because it has unpaired electrons. You see unpaired electrons. I don't. I see lone pair, lone pair, lone pair, lone pair, bonding pair, bonding pair. Where are the unpaired electrons? That's because valence orbital theory, which is what we do all the time, have been doing, valence orbital theory shows us all of them paired. Well, that's a failure. It's actually got 2 unpaired electrons, and if you do molecular orbital here, you'll see that it has 2 unpaired electrons. Okay? Which is needed for it to have magnetic properties. I don't know if I mentioned that. It was on the original handout, but I think sometimes I don't mention it. Go back to handout 1. It'll say comment about MO theory. All right, from about week 1. Okay. Resonance structures. More common way to show what's going on. In this approach, we show multiple Lewis structures for the same compound with only the pi electrons move. Again, this intro is sort of intro theory. Once we get sort of past this page, we'll start kind of doing it. We've got to say some sort of broad intro things first. Okay, what are we under here? That was a B. What was A and what are A and B under? Somebody got it? I need to know where we're at. Hopefully you need to know where we're at. Where we're in. A and B fell under 1. Neutral conjugated alkenes. All right? Okay. This is a neutral conjugated alkene. You see where we're at? I have to see where we're at. Okay? These are strategically designed handouts here. All right? Right? Okay. Can we do resonance of this? Resonance of neutral conjugated dienes or polyides is actually a little bit difficult because you don't have any charge or polarity to sort of guide your electron movement. All right? but it's the most sort of intro, so we're sort of beginning with what may be the most difficult. That's because the theory here is best looked at here. All right, well, let's kind of do it. How can we move electrons here? First off, the orbital view we've already done. Same above, except one did not have the methyl on. But by the way, the compound that has the methyl, the extra carbon, how many p orbitals does the extra carbon have? 0, because it's sp3. The only reason I put the extra methyl on the one on the left is because the one on the right, I think, had an extra carbon. But the one on the right, the extra carbon was between the two alkenes. All right? The one on the left, it was on the end. But here we just got rid of that. We just have a diene. How can we move electrons? All right, let's start doing some of that. We can take the pi bond here. All we're moving is pi electrons. We can move these electrons here. What does that mean? I'm taking this and I'm moving these pi electrons out onto the carbon to become what? Yes, it's a lone pair. And so that arrow movement leads to what? Lone pair here now. Not there. And charge. What's the charge here now? How many H's are there? 2. Charge here now. Negative. Charge here. Positive. There's only one H there. It's positive. All right? That arrow movement leads to this. Now here's a reason, the major reason I don't do all this during week 1, because during week 1 you guys are very slow to recognize charges or determine them. You're very slow to recognize where hydrogens are and doesn't even know that there should be charges here. You don't know what a mechanism arrow means, and so that arrow is not much use to you. To me, at this point, we can know what I just talked about, and we can focus more on the theory and understanding of resonance. All right? So, what is this? That's a resonance structure, because all we did is move pi electrons. If I agree, all we did is, it's a different structure. All we do is move pi electrons. It's a resonance structure thus. Resonance arrow here. Whenever we go between resonance structures, we use a double-headed arrow called a resonance arrow. If we had just used a single arrow, probably don't draw this, that means we're converting this molecule to that molecule. That's like a reaction is, right? We're not doing that. And if you had done something like that, what type of arrow is that? It's an equilibrium. This ain't equilibrium. It's resonance, and we use that type of arrow there to indicate that's what we're doing. All right. Let's keep going. Can we show another resonance structure? By the way, what if we move these electrons in here? What would that do? That would give this back. What else can we do here? Well, I'm sort of showing you for the first time, and then we'll start doing this over and over. What else we can do here is we can take this pi bond and move it over here. And that's kind of, I think I'll call that the windshield wiper. All right? Move it over here, and it could come back. Windshield wiper, right? Let's move it over there. Now, this is not going to be a lone pair over there. You got to understand this movement. It's just the pi bond moving from here to over there. All right? Now that I've told you that, what do we get? Boom, boom, boom. Nothing happened on the end, so we should still have lone pair and minus. What's now between carbon 2 and 3? Pi bond. What's over here?
Positive charge.
It's missing the pi bond. It has 2 H's. That's a positive charge. And lo and behold, what do we call the one on the right? It is a third or another resonance structure. You can be careful with terminology or whatever. How many resonance structures on the board?
2.
You got to be careful. You might ask for clarification. There's 2 resonance structures of the original. I'd say that's 3 total resonance structures. That's not going to mess you up. I'm just getting you to make sure you probably need to clarify that question. We've drawn two additional. Would you call this a resonance structure? It is a resonance structure of those. I mean, okay. Can we draw another resonance structure? Now we actually could. We could leave this the same, and what if I just move these here? Well, what does that do? I'm just moving pi electrons. That would give, that's a negative. What's now here? And charge? Negative. What's here? Positive and here? All right. Now this is starting to get what I would say ugly. Because at some point we're going to step back and say, of the four structures on the board, which resonance structure is the best? The very first original one drawn is the best. Why? More stable? The answer to that is yes. You got to be careful though, because to me that makes me think that some of the questions just have to be clarified, and if you take the question the wrong way, you're going down the wrong road. This is one compound. So when you say it's more stable, then that means perhaps another compound is less stable. Yes, this is more stable, but you got to know that it's really only one compound. This fake structure is more stable. Okay. Basically, if you were asked to draw this compound, how would you draw it? Would you draw it 1, 2, 3, or 4? 4. Count it backwards. This is the best. Why? Less charge. Charge separation leads to higher energy. Okay. Why is this? Another reason this is better. More bonds. Every carbon has an octet. Here the carbon doesn't have an octet. And remember on week 1 we were really trying to get octets because that's the driving force of bonding. Okay? That's 3 additional resonance structures, but they're not as good as the original. Basically, again, theory here. We just did a little on the board drawing resonance structures, which we'll do more and more of. Go back to theory a little bit. What do we have here? We have 4 carbons in a row, and each carbon has a p orbital. Agree?
Yes.
And that is the answer for all of these. P orbital, empty p orbital with a lone pair. Why is that lone pair in a p orbital? Because anytime a lone pair is next to a p orbital, we want to be in a p orbital. There's a p orbital here. Okay? Every one of these has 4 p orbitals, 1 on each carbon. Here's at this point is where we go back to molecular orbital theory a little bit. 4 p orbitals and 4 electrons. Everybody agrees 4 electrons? You said, why is there not 4? And I said, there are 4.
Yes, I see.
It's 4. When you get to molecular orbital theory, here's what you'll do. You'll just say, ultimately, there's 4. Now, there's 2 MOs, so it's a little bit off, but here's the gist. Put those 4 electrons in here however you want. What if I put 1 here, 1 there, and instead of putting 1 there, put 2 there? What if I do that? I said any way you want. Well, guess what? That looks like one of those. Which one? That's actually the second one right here. 1 electron, 1 electron. No electron there, and 2 on the end. All right? Put them in another way, any way you want. What if we leave that one empty, put 1 here, and put 2 there? I think that's the third one. And guess what? What if we put 2 there, none there, and 2 here? Did we even draw that one?
No.
We didn't draw that. But guess what? We could have. How would we have gotten to that? Right here. Instead of moving this over there, if I had taken this and moved it here, it would have put a lone pair here, and we had a lone pair on each end. That would have been that? Yeah, we could have did that. I could move those arrows like that. Basically what you have here is Once we have a pi system that's conjugated, it becomes one system. And the electrons are in there. But how are they going to be in there the best way? Best way is for them to be in there like this. 1, 1, 1, 1. And what is that? Which structure is that? That's actually the first one. But they can be in there the other way as well. And at this point, it becomes just sort of like one thing, but it's just sort of moved a little bit. Again, there's not much polarity here to dictate us. All right? And again, I'm doing a little bit of theory here. You can't just teach theory by telling you 15 minutes of stuff. It's not theory. It's just random facts that you guys have trouble with, okay? But if I talk 15 minutes of theory, it's just going to lead to all types of questions. That's good. You keep thinking about it, get your questions. Eventually, we're going to move on to less theory, and we're just going to be doing questions.
Did you say there were 2 MOs here?
There's more than one. There's actually 4.
So you don't want us to worry about that?
Don't worry about it. There's actually 4 MOs here. But each MO is spread over the entire molecule. Okay. Before I erase this, some golden rules of resonance. It's on the back page. It's free information. All right? Or the next to the last page. These are your rules. Don't break the rules. For example, one of the rules says all resonance structures have the same net charge. What's the net charge of this guy? It's neutral. Then all resonance structures better be net neutral. What's the charge of this? Net neutral. It's balancing. Charge of this? Net neutral. Net neutral. You see? If you ever end up with a resonance structure that somehow has a different net charge than the others, you've got something wrong. You're either missing a charge or something is wrong. There's other golden rules. All we moved is pi electrons. Did we ever move sigma electrons? No. If you move sigma electrons, you ain't doing resonance. If you move sigma electrons, you're making a new compound. All right, resonance hybrid. Resonance hybrid is hard to draw here, but the key thing is, I told you the electrons are spread all over. Really, you have a system that looks like this. Pi electrons are just all in here. Okay? How many? 4 pi electrons? And I'll use my garden hose analogy, a hose pipe. If I brought a hose pipe in here and sort of turned the water on and the other end was closed, it would fill up with water. I agree? And maybe it's 20 feet long from here to the wall. It would fill up with water. How would that water be distributed within that garden hose? You would think, what do you mean? It would be all full. Or would half the water be down there and the other half of the garden hose be empty? No, it would fill it up completely. I mean, it's almost so obvious, it's like, I don't understand the question. The water would equally distribute throughout the entire 20 feet of garden hose. Everybody think you agree? That's what you got here. The electrons are equally distributed throughout here. And the main thing we can point out now is there pi electrons between carbons 2 and 3? And the answer is yes. All right, the electrons are spread out all through here. There's pi bonding in here. What did we say resonance was also called? Delocalized bonding or pi bonding. There's pi bonding between 2 and 3. We can't see from the static structure, but we see from the p orbitals overlapping. We see from this discussion. We see from some of the resonance structures. This resonance structure shows us there's p orbital overlap between carbons 2 and 3. This is sort of the resonance hybrid, okay? The resonance hybrid is going to have partial bonds. That is, what is the bond order? What's the BO between carbons 1 and 2? How many bonds between 1 and 2? And the answer is 1.5. With the full bond shown, and this is a half a bond. Now, the 0.5 is always going to be right and a half. You might argue sometimes we might argue maybe it's 1.75 or maybe it's 1.25. We're not going to get that precise in our quantification. If it's between 1 and 2, we're going to call it 1.5. All right? How do we get the resonance hybrid? We sort of add up all of our resonance structures. For example, between 1 and 2, how many bonds between 1 and 2? No, here. 2, double bond. On day 1, you said 2 bonds, right? How many here? 2. But how many here?
1.
Only 1. So if we start averaging, we now have a total of less than 2. How about over here? Only 1. And if you start averaging, what's the average of 2, 2, 1, and 1? 1.5. Actually 1.5, exactly. In some cases, it may not be, like I said, but we're still going to say 1.5. What we'll see is your hybrid comes from averaging your resonance structures. I'm not going to do any charge here because, again, it's not as easy to work with this. Let's see where we're at. Yes.
The pi electrons that are located on carbon 4, with the structure you drew on the board with the dots, could they ever be found on carbon 1? Are they moving like that across the molecule?
What do you mean, are they moving?
So the way you drew those dots, it makes me feel like the pi electrons that are on carbon 4 could sometimes also be on carbon 1.
Well, first off, these are not supposed to be electrons. This is a bond, but instead of showing a full bond, I showed a partial bond.
Oh, okay.
And a partial bond is shown not by a full line, but sort of a dashed line.
Okay.
It's like a half a bond.
Okay. So those pi electrons will never be on carbon 1.
Well, let me go back to the garden hose. If I put water in it and fill the garden hose up with water, you got water on this end, you got water on that end. It seems like you're trying to say, will this water ever be on that end?
Yeah, that's what I'm asking. And
Well, eventually
yes.
it may diffuse or migrate or whatever you call the term. And it's all water. It's all in there.
So yes.
And again, and I think in the real life we say electron density. Semi yes. I don't know about moving electrons. But it's all in there. It's one system. And the electrons, problem is you don't want to say they're moving back and forth. That starts to get into trouble a little bit. Okay, homework. Total number of p orbitals here, total number of pi electrons in the conjugated system. For each carbon-carbon bond, what is the bond order? Expected bond order. Think about that. Major, minor resonance structure. So in like the ones we drew, that would be called the major resonance structure. The best one. We say that's the major one, or best. Those that are not as good, we call them minor resonance structures. And we'll be doing more of that. Okay, resonance stabilization of cations. Cations are a little bit easier, a little bit more intuitive. Theory and then resonance. I reckon let's do resonance first. How do you stabilize a cation? And I think we asked these questions early on. Move electrons towards it or away? Towards it. What electrons can we move towards it? We can do the old windshield wiper and move these over here. Boom to boom. What does that arrow movement give? What does it give? We now have pi bond over here, yeah?
Positive.
Positive where?
To the right.
Because if this structure is positive, our resonance structure should be positive, right? There you go, there's a resonance structure. Can you draw another one?
Could you make like a negative on one end, positive on the other?
Of the pi bond?
No. Of the whole molecule. Like move the pi electrons to the first carbon.
Move this here
No. From that structure that you just drew.
to here?
No.
Oh, here.
Yeah.
Move from where?
Move the pi electrons to the first carbon.
Here?
Like that, yeah.
Okay, we could theoretically do that, and that would give a resonance structure, but we ain't going to do that from now on. Because look at it. If we did that, we would get negative here, positive, and positive. Is that right? Yeah? That is theoretically a resonance structure. But is it good? Which one's the worst up there?
On the far right.
When we drew. And because it's so bad, we're not going to take time to ever draw it. Typically when you do resonance, you want to do better things. Like this is why I would want to do it. So yes, good. Theoretically a resonance structure, but it ain't a good one. And resonance needs to be something we want to do. What have we done here? Which one of these is better? These are actually the same. Same energy. We're getting close. What is the hybrid going to look like? A, B, and C. Here, between A and B is single bond. Over here, it's 2 bonds. So what's the average? 1.5. What's the average between B and C? Not double, not single. 1.5. Okay, in the hybrid, the VO equals exactly 1.5 between each carbon. Charge. What's the charge on this carbon, A? In the hybrid. Here we're doing charges for the first time. What's the blend of +1 and neutral?
Partial positive.
Half a positive. We call that a partial positive. This is neutral everywhere. What's the partial charge here?
Partial positive.
Partial positive. And those add up to a full 1 positive. This compound is full 1 positive. This is a resonance hybrid. Okay? If you can see this compound, this is how it would look like right here. If we can take a picture of it. Then we ask, well, why do we draw it like this? Because we don't like to draw these partial bonds in our day-to-day life. We save the partial bonds for when we have to talk about really what's going on. Okay. Day-to-day life, we like to use these full bonds. But what we do is we show 2 different fake forms. These are actually fake at this point. And we say, you know what, guys? The true structure is somewhere in between. And there it is over there. I think we got a minute left. I want to get this. Let's go back to the theory. How many p orbitals do we have here? 3. Because there's an empty one here. Right? Empty p orbital. Hybridization. Okay? This is 3 p orbitals overlapping. How many pi electrons? 1, 1, and empty. I'll draw a positive there to indicate that it's empty. That's what you got here. Well, go back to what I said earlier. You can't maybe write all this down, okay? 3, that becomes your conjugated system. 2 electrons. Put them in any way you want. How about 1 there and 1 there? Did we draw that structure? No, because that would be very bad. You'd have a diradical and you got lots of charges. Let's keep them paired. Let's keep them paired and, well, those would not be able to bond. Let's let those bond and leave that one in. Well, we got that up there. It's the first one, right? Or it's this one, right? So that looks like you can make a pi bond, leaving that empty. We're back to the same thing. You can put them in any way you want. It leads to your resonance structure. It's one system. At this point, look at the cues along the way, what questions to ask, the theory, and we'll be consistent. We'll ask the same type of questions. We'll do the theory, the structure, and we'll draw resonance structures. And we'll talk about the hybrid. That's resonance right there. This is intro. Next time we'll do more. We've got the rules for resonance, but next time we have tests. Video key will be posted later today. Okay, guys, have a good day.
As long as you don't get the gear all over.